So I bet Monica is going to brush her teeth after drinking, what is that? Red, some lemonade thing, right? I mean, these are pictures of, I think, probably kids' mouths, right? And some kids who just don't drink don't brush their teeth after drinking Mountain Dew and stuff. Isn't that just disgusting, right? No, they're kid mouths. 'Cause this is due to Mountain Dew or due to Coca-Cola. So they're taken at the dentist's office. And how long would that take? I should have read the small print, right? I bet you the Coca-Cola one, I bet you it doesn't take that long because the kid's not brushing their teeth at all, right? And that stuff just sits in there and eats away at the enamel and ugh. So, or you can, right, what happened with the finger here? Right, look at that. They spilled concentrated sodium hydroxide on themselves. Dang, we're going to be working with concentrated sodium hydroxide in lab this week, so, right? So if you don't follow appropriate safety protocols, right? Ugh. But, hunky-dory, things are nice and happy when you use them correctly, right? In fact, they make life a lot better, right? Whether it's Tums or cleaning supplies is a very typical acids and bases, right? So, strong acids. Let's take a look at an animation of a strong acid. Okay, hydrochloric acid, HCl, is a strong acid. So you can see what the molecule is. It has this shape. So they're going to zoom in and see what these molecules do in solution. And it happens a lot faster than this, but pretty much just end up with chloride anions floating around and a whole bunch of H+ floating around. Are there any HCl molecules even left, Romero? No. So HCl is which strong acid, right? Because it generates a whole lot of H+. Let's take a look at something else. Hydrofluoric acid is what they call a weak acid. So you bubble it in. They should have chose different colors for the fluoride, but that's okay. So you bubble in, you have little HF molecules flying around, and it looks like, oh, there's one. See, one little H+ came floating off. Okay. So hydrofluoric acid is a weak acid. The whole acid thing is just the population of the H+. And we kind of found out last class period, though, Eric, that we're not supposed to say H+. In nature, it's really what? H3O+. What was the name of it? Hydronium. But it's kind of like sig figs. We talk about it once, and then we just kind of, oh, yeah, it's there. Good to know, but we never really use it. So the terminology, Brandy, strong acids are what % dissociated in water? 100. Yep. Okay. There are a gazillion acids, but only how many of them are strong? 6. So if we know the 6 strong acids, then by default, everything else has to be weak. That's why we know the 6 strong acids. Okay. So, Monica, can you name one of them? Or give me one of them. HCl. In fact, the halogens are going to give you 3 of them. HCl, HI, and HBr. It's weird. It's all of those halogens, but not HF. HF is the most electronegative element known to man. It just sucks up the electrons, and that H has a hard time leaving. It's too polar. HBr is, as you go down, it gets stronger and stronger acids because they get less polar. So HI is stronger than HBr, which is stronger than HCl. Okay. It's kind of odd that a strong acid can be stronger than the other one, but we have the other 3 to do. Do you recognize any acid formulas? Eric. Ooh, slow down. HNO3. Now you're close with HSO4. Sulfate has a -2, so it's really H2SO4. There's one more. Has a whole bunch of oxygens, just like all these other guys have oxygens. Perchloric acid. Ooh, all right? Perchloric acid. Whole bunch of oxygen. That's going to be another hint what's coming up. Before we go to the boards, we'll see some trends, some general trends for strong acids, what makes an acid strong. A lot of oxygens is one. So, Summer, she had to go somewhere. Mari, if an acid is not strong, then it's considered weak. How can you easily recognize if an acid should be considered weak? Yeah, it's not on the list. It's not on the list. Or not in the list. That's why you know the 6. In general, for strong acids, we can write HA, in general, breaks up into what, Maria? H. Yeah, H plus A. Now we need to put little charges on these guys. H, you'd put a plus, and A, you put a negative. Right? Now we could also write that as, in fact, this is how we're supposed to write it, but I think this is the last time we ever will. Ramiro, how else could we write that? Yeah. Exactly. Right? But this is how we're going to be writing it all the time, just because it's too much work to keep adding water all the time. Strengths of conjugate acids and bases. So I'm going to be giving you this table, Alyssa, and we're just going to practice using it a little bit. Which conjugate acid listed is the strongest? All right, do you see it? Look at the very top. Do you agree with her? There it is. If you're reading the table right, that's right. Which conjugate base is the weakest? Oh, who have I picked on? I guess Eric. Everybody agree? Yeah, according to that table. Okay, I could keep asking you this same question again and again and again, but let's see if we can draw the trend just from what we just did. The stronger the conjugate acid, then the weaker the base. Yep. How about this one? Mari, which one is stronger? Let's see. I see H2SO3. The middle-ish. So the stronger one has to be H2SO3. Yeah. Okay. How about, can any compounds in the table act like an acid or a base? Brandy, is there anything in there that can act like an acid or a base? Well, give me an example of one. Yeah, it can act like an acid or it can act like a base. See, it has to be in both sides there. I hear HS negative. Hang on. Here it's here. And where is HS negative? Well, it's in there somewhere. Where is it? God, no, I'm so blind. Here it is. Thank you. Right? HS negative can act like an acid or a base. It just depends on who it's with. Right? It can have acidic or basic properties. HS negative can. Okay. So life often isn't as simple as it looks. Predicting acid-base reactions. You have to add an acid plus a base, then you get an acid and a base. Acid-base reactions, Ramiro, are always of the form above, and the reactants are always blank of the products, like this guy and this guy. What's the word for that? Conjugates. Right? The predominant direction. Okay. We're supposed to think of equilibria as dynamic. In other words, you're supposed to think of it as having a double arrow. Right? But they want you to say, no, I want you to indicate, are there more products? And if so, at equilibrium, if there's more products, the arrow should be pointing at products. If at equilibrium there's more reactants, I want the arrow pointing towards reactants. They want to show, that's what they call the predominant direction. Okay? So the idea here is we're going to draw an arrow towards the products or the reactants that just points toward the which acid? Why is it weaker? Because why? It's the weaker acid, so that means it does dissociate or doesn't dissociate? It doesn't. All right? You're halfway there, though, Ramiro. You're halfway there. It's the weaker acid because it doesn't dissociate. Once you form it, it stays there. It's like a lug, just sitting there doing nothing, right? Worthless. Sitting there doing like a precipitate. Just sits there. So weaker acids, once you form them, they're stuck. Things like that drive reactions. So you can form a weaker acid. So you compare the two acids on that table. I don't know, let's say this guy's weaker on the table. Well, then you point the arrow towards the reactants, if that's the case. Okay, that would be the predominant direction. At equilibrium, you're going to have mostly reactants, hardly any products. Predict the products and direction of each reaction. Okay, let's keep it like that. So Maria, first let's predict the products. What plus what? So now what's the game plan? We have to have an acid and a base over here. And they have to be what? They have to be, the C word, conjugates. Okay? Now I'm going to start with the complicated one. Can he go either way? You don't know if you should write S minus 2 or if you should write H2S. Either one. So don't start with him. Because you go either way. You have no clue. Start with him. This compound can only be a what? Acid. Why? Why is that an acid? This can't be a conjugate base. Why is that a conjugate acid? It's fully, no. Dissociated means things falling apart. It's fully well, I guess that's chem speak. Fully protonated. It has all the H's it can take. It's maxed out on H's. That's an acid. That's the only way it can go. It's got all the H's it can take. This has to be an acid. Okay? You can't add it. It can't take on any more. That's what bases do. This can't take on any more. So that has to be an acid. So on the other side, I have to write its base. This guy, he must be a base because he's reacting with a acid. That's how you figure out what these guys who don't sure what they are. All right. So on this side, you have to write as acid. Okay. Let's go ahead and write that one first. What's the conjugate acid of HS minus? It would be H2, and you got to add a plus. So a plus 1 and a negative is 0, so just H2S. And then we need the conjugate base of H2SO3. HSO3 with a negative, because you have to take away a plus. Subtract 1. Take away a plus. Subtract 1. 0 minus 1, negative 1. Okay. Now we have to compare what and what, Mari? Yeah, which ones there? Which acids are we going to compare their strength of? Which acids? The H2SO3 and the... No, that one we said was a base. Yeah, the H2SO3 and the H2S. So looking at that table, which one is weaker? H2S or H2SO3?
H2S.
She says H2S's. Alyssa, that's right? Okay. H2S's. All right. So that's how you predict the products and the direction.
Are we going to be given this?
Yeah, you have to be given that. Except Eric. All right? He's got a photographic memory. Try this one. Write down the products and the direction. I went to school with a guy with a photographic memory. That just sucked. All right? Yeah.
Really?
Asked the guy after the test, how'd you do this one? How'd you do that one? And his eyes would just kind of blank out. Then he'd say, on page 93, it was on the third paragraph, because he was just flipping the pages over in his head. It sucked going to school with people like that. Or a person like that. It's the only guy I ever met that could do that. So identify what's acting like what. Predict the products. No, you can have base plus acid or acid plus base. It doesn't matter. A plus B is B plus A. Okay, let's pick on Brandy. Brandy, which reactant doesn't have a choice in its properties? HCN. It has to be a acid. Fully protonated. So that means we have to write its base over here, which would be, everybody, CN negative. Okay. The other guy has to be a base. So if it's going to be a base, it's going to form H2S. That's got to be an acid. Okay. Now we have to compare the two acids. Hopefully you did that. Ramiro, did you compare HCN and H2S? Okay, which one's weaker? He says HCN is. Okay, everybody agrees with you. So I'm going to draw the arrow back there. All right? Okay, before we go to the boards, just one last topic. Predicting acid strength from molecular structure. So these are just general trends. And they're going to give you some molecules and you're going to say, okay, which one's more acidic? So the first bet, I would just look at the darn table, right? But odds are they're not going to be in the table. So you're supposed to just be able to look at them and tell. So let's see how this works. For elements X that are in the same group in a periodic table, the larger the element X is, then, okay, so you have this bond, and they're making X bigger and bigger and bigger and bigger. What happens to that bond? As X gets bigger and bigger and bigger, the bond gets, kind of longer. It gets stronger or weaker? It's dispersed over a bigger area, right? This bond is dispersed over a bigger area. The bond gets weaker, right? As that X gets bigger and bigger and bigger, the bond gets weaker. So that means it becomes a what acid then? If that H is getting weaker and weaker and weaker bond, the acid is becoming steadily stronger and stronger and stronger. Right? The bigger that atom is. Make sense? Easier it's going to fall off. Okay, for elements that are in the same period, the more polar the bond, then the what? The only hint I can give you is looking up here on the periodic table, we have 3 strong acids for halogens, but HF wasn't. Why? F is really, really electronegative. It's a very, very what bond? Extremely what? Polar. So polar does not help things get acidic, right? So that's how I remember this stuff. So the more polar the bond, then the weaker. So I try to make some logic to this. The more oxygens, there's some logic to that one too. The more oxygens present in the molecular formula, look at half of your strong acids. Look at all those bloody oxygens. So odds are, the more oxygens, stronger the acid. Alrighty, so we can go to the boards, enjoy ourselves, help each other out, get out of here, and then you'll have a weekend. I even have some chalk. It's in pieces, but it might be longer than what you have available. Here's the first one. Use the table to decide whether the species on the left or those on the right are favored by the reaction. So they want you to draw the arrow, indicating the predominant direction, right? Same type of chem speak. Is what's on the left or the right? Are the reactants or the products more favored? So remember the game plan? You have to compare the acids. You have to figure out what's acting like an acid in there on both sides. Then compare the strengths of the acids. Exactly. No one's noticed this. I gotta erase it before everyone sees it. Did you see that? It's all right there for you.
They were right?
I don't know. I assume they were right because they're probably talking to the folks around them. Okay, Eric's got it going to going to products for the first one. I don't know if he's right or not. So does Ramiro. So if you're saying that, you're saying, let's see, he's got to be a base. So he's got to be an acid. He's got to be a base. He's got to be an acid. So the top one, if you're drawing it towards products, you're saying that water is water is a weaker acid than HCO3 minus. Is that right? Okay. All right. So water must be H2O, weaker acid. The next one. He doesn't have an answer down there. Well, you can change the rule to what you want to follow. I just always approach it the same way. I always go by the acid. So hopefully you compared water with that aluminum aluminum with 6 waters on it, right? So which one is stronger? Sorry, which one's weaker there? H2O is? Okay. So both of them are pointing towards products then, huh? Because it always points towards the weaker acid, and H2O must be weaker than, that's what Alyssa said, it's weaker than that one. So.
This is AlH2O3 plus. That one's just 0.
Oh, I'm missing it. I am missing it. Sorry. I'm missing it. I forgot to have it in there. Try the next one. These are making sense. Try the next one. Mari has the B and 48 going to products. So does Jessica. Going to products. H2CO3 and H2S. There's H2S and H2CO3. So which one's weaker? H2S is weaker. It should go towards H2S. Where's H2S? So you have to base it off your 2 acids. And he's acting like a base. So you have to go off your 2 acids. So you have to go by H2S and H2CO3. And H2S is a weaker acid than H2CO3. You have to go by what's acting like an acid. He has to be acting like an acid. Yeah, that's H2. Here's H2CO3. And yeah, there's H2S. H2S is just barely weaker. Yeah, see if you can get all these figured out. You can get out of here early, man. That's cyanide and water, like HCN and hydroxide. Yeah, it can't be there's no H, so it can't be an acid. So she has it going to the cyanide side. Does it have it go? Okay, so it is brandy. Okay. Folks are having this one go to the cyanide. All right. How about D? What did you have for D? Going towards the reactants again? All three are going to the reactants. Huh, I didn't know that. Okay. Okay, so all three are going to reactants. How about this last one? What you need to do in the last one is circle the compound that is the stronger acid, right? They give you two compounds. They want you to identify the stronger one and say why. So you're comparing H2S and HS minus for the first one. Identify the stronger one and say why. I'll see if everybody agrees with you. Because it's not, this is in problem 1551, I just picked A, B, and D. Yeah. Yeah, I just picked those. So pick your answers, and then we'll pick on you to see if we can get consensus. Alyssa, just scribble up your answers so we can pick on you. Eric, scribble up your answers for this one. Let's see if everyone agrees with the same thing here. I think most everybody has H2S for the first one. All right. Everyone have an answer? So I agree H2S, but why? More H's? Yeah. That's a good one. More H's. That's probably the best explanation. More hydrogens. How about B? Okay, yeah, okay, that number of oxygens is the same, number of hydrogens is the same, so you got to compare SE and S, and I think that's where it's headed, right? These two. Which one's bigger? SE. So which one has a weaker bond? The SE one. So which one's a stronger acid? The SE one. Yeah. Not polar. It's size. They're interested in size. The polarity thing really only works with these halogens kind of stuff. Everything else is so weakly electronegative, there's really not much there to talk about. There's only one left. You picked 4 O's because there's 4 O's, yeah, in comparison to 3. Very good. Have a good weekend.